Do you remember when we first met complex numbers, we said that every quadratic equation had 2 roots and every cubic equation had 3 roots? Well, we said it, but how would you prove it? Now, in this program, we're going to prove that. In fact, we're going to prove something much more ambitious, something that goes by the grand title of the fundamental theorem of algebra. Now, this theorem states that every polynomial of degree n has precisely n roots. Well, that's a bit of a mouthful. What does it mean? Well, this is a polynomial of degree n, and these are the coefficients of the polynomial, and a root is a value of x which makes this expression equal to 0. Now, some of the coefficients could be 0, but I'd rather not have the first one, an equal to 0, because then it wouldn't be a bona fide polynomial of degree n. So let me assume that an isn't 0, then I can divide through by it. That won't affect the roots. And I'll get this expression. And of course that's nice because it assures me that I have a polynomial of degree n. Now, remember, in complex numbers we saw that some of the roots could well be complex, and a surprising thing about this theorem is that we even allow the coefficients to be complex, and it's still true, and so I allow for that in the notation by using z, and the coefficients c, n minus 1, etc. can now be complex numbers. My theorem says that such a polynomial has precisely n roots. That is, there are n complex numbers, alpha 1, alpha 2, and so on, such that f of alpha 1 is 0, f of alpha 2 is 0, and so on. In fact, the theorem that we're going to prove, for starters, seems a lot less ambitious. We're going to prove that this polynomial has at least one root. Well, it seems a lot less ambitious, but it's very easy to get from one root to n roots, as we see later on. Now, in this polynomial, I'll take the coefficient c0 to be non-zero. Well, why do I do that? Well, you see, if I have c0 equal to 0, then it's immediate that there is a root. It's z equal to 0. And so the theorem would be proved. There would be nothing to prove. So in order to have something to prove, I'm going to take the coefficient c0 to be non-zero. So now we know what this first theorem we're going to prove is. It states that a polynomial like this has a root, alpha. Now, our proof is going to be very visual. That shouldn't surprise you because complex numbers are themselves very visual. So in order to see what sort of pictures we're going to need for the proof, here's Colin.
Well, we already have an excellent picture for complex numbers as points of the complex plane. But how are we going to picture the function f? Well, supposing I take a point of the complex plane, a complex number, I can substitute it in the expression for f, and you know how to add and multiply complex numbers, so you get an answer, a complex number, f of the one you started off with, say that one. And if I take a second number, then I get a second answer, and if I take a third one, I get a third answer. Well, I worked those points out before the program using a particular cubic polynomial that we've got in mind. But as you can see, the picture isn't very helpful because the points and their images are getting all mixed up. We can correct that easily enough. We'll use two diagrams. On the left is the domain Z with complex numbers before they're mapped, and on the right is the codomain with the images f of z. Let's add more points and their images. What's this? It's a complex number that's mapped to 0. It's a root. Let's look at that again. We had a point in the domain whose image in the codomain was the origin. That's a complex number z such that f of it is 0. And that's what we mean by root. It's a number that's in the domain that's mapped to 0 in the codomain. And that's how we can tell when we've got one. Well, this cubic polynomial we've been using should have 3 roots, and we might hope to find them this way, but it's a bit hit and miss just choosing points at random. What we really need is a systematic method for searching. One way is to look at all those complex numbers with the same modulus. Of course, these lie on a circle. But how do you know if there's a root? You look in the codomain. Does the image curve pass through 0? This one doesn't. And if you try a different circle, well, neither does this one. No roots have shown up yet, but don't worry, because you can now see how to systematically search for them. We start with a small circle. It has a small image. Now we grow the circle outwards, watching the image curve. This one hits the origin, so somewhere on the circle there's a root. But we don't know where on the circle, but we can find it. Remember, what we're interested in doing is proving the existence of a root, not actually finding it. So, as soon as this curve crosses the origin, we know we've got a root and we're finished. So that's what we're going to do. We're going to systematically grow a small circle to a bigger circle in the domain, watch the image curve in the codomain, and when it crosses the origin, we know we've got a root.
Well, this searching process will certainly find us the roots, if there are any. For our cubic polynomial, there were roots, and we found them that way. But we're not interested in finding roots. We want to prove that there exist roots in general. Well, we'll get a clue from our cubic, not by looking at what happened at a root, but seeing what happened a little bit before we hit a root and a little bit afterwards.
Let's look again at the search for roots. We start with a small circle. In the case of our example, the image is a small curve. As we grow the circle, this image changes. As we pass a root, the image encloses the origin. Let's see that again. So, for this small circle, we had this image curve, and for this larger circle, we had this image curve. And as the circle in the domain grew from this curve to this curve, the curve in the codomain deformed continuously from this one into this one. And now, if you look at these curves, you can't deform this one into this one without it crossing the origin, because this one doesn't enclose the origin, whereas this one does. So, if we can show that this sort of behavior happens for any general polynomial, then we'll have proved the theorem.
And so that's how we must prove the theorem in general. We must show that we start with an image curve in the codomain which doesn't enclose the origin, and we end up with one that does, and so it must have cut the origin. Well, we know our sample polynomial behaved that way, but can we prove that every polynomial behaves in that way?
When the domain circle is very small, then the image curve is also small. And in the case of our cubic polynomial, it's a curve that's very close to the point which is the constant term of the polynomial. Well, does that happen in general? Yes, it does. And you can see that just by looking at the formula. Because you see, here's f of z. When z has small modulus, all its powers have small modulus. In fact, rather smaller modulus. And when you add complex numbers that are small together, you still get something that's small. So, for an approximation, we can ignore everything except c0, the constant term. So what does that mean? For a small circle in the domain, the image is a small curve close to the constant term, c0, and c0, remember, is non-zero. So this is a small curve which doesn't enclose the origin. And that's half of what we wanted to prove. If we can prove that at a later time the image curve has to enclose the origin, then we'll have finished. So, for a clue to that, let's look at our sample cubic polynomial once again. We'll start with a small circle as before. We're not interested in roots this time. We need a change of scale, and we'll concentrate on the image curve. The radius of the circle is 3 units. Let's keep that fixed and change the scale. Now we'll continue to grow the circle while you watch this image curve. we'll need to change the scale more than once. Our circle has radius 37, but this image curve has been scaled by a factor of almost 1300. On the same scale, we wouldn't even see the circle. But what's happening to the image curve? It's getting more and more regular. It wraps 3 times round for once round the circle. Imagine a point tracing the circle just once. The image is beginning to look like the curve for z cubed. This is z cubed. It's wrapped round 3 times and does enclose the origin. And our curve is getting closer to z cubed. So, when the circle in the domain was very large, then the curve in the codomain was much larger and went 3 times round the origin in a nice regular fashion. In fact, it behaved like z cubed. Well, that's very suggestive. Maybe the 3 has something to do with the fact that we chose a cubic polynomial. Well, indeed it has. When z is very big, has large modulus, that is, all the terms except z to the nth will be negligible compared to z to the nth. Z to the nth dominates the polynomial. So, for an approximation to the polynomial for large z, we can use z to the nth. Now, perhaps you know that z to the nth behaves in a very nice fashion. This is the case for z cubed. The box will record the number of revolutions, 3. This is z to the 4th, 4 times. This is z to the 5th, 5 times. So, what have we got now? For a small circle in the domain, the image is a small curve in the codomain, which doesn't enclose the origin, and for a large circle in the domain, the image is a large curve in the codomain, which goes n times round the origin and does enclose it. As the circle in the domain grows from small to large, the curve in the codomain deforms continuously from this small circle into this large curve. And as it does so, it must cross the origin. So somewhere between here and here, the curve crosses the origin. So somewhere between here and here, there's a root. And that's what we wanted to prove. So that's the basic idea of the proof. A proof by pictures, but nevertheless a proof.
So that proves our first theorem that every polynomial has a root. We've proved it. Or have we? Actually, there are a couple of technicalities. That's just mathematics for snags. The first snag is this. As we grew from here to here, if we did it by a series of jerks, well, it's possible that we might have missed the origin altogether. Now, in fact, we do this continuously in the case of a polynomial. There is a smooth transition from here to here. And that's why this theorem applies to polynomials, because this growing is continuous. Now, the second snag is perhaps more serious. It's certainly more interesting. So here's Colin to tell us what it is and how we can overcome it.
Well, we can see what the snag is if we look at this curve. It's a nice smooth curve, nothing particularly remarkable about it. But does it enclose the origin? Supposing it does enclose the origin. Well, our proof depends crucially on not being able to deform this curve into a small curve without crossing the origin on the way. But watch this. So, if that's what we mean by enclosing the origin, then our proof's all wrong. Well, what we need is a definition, a precise definition of what we mean by enclosing the origin, which excludes curves like this, but if it's going to mean anything at all, then a curve like this, a straightforward circle, has got to enclose the origin. So what's the difference between these two curves? We can get some clue as to the difference if we look at the way a point traces round them. You see, if you go round this curve, you start to go round the origin one way, and then you begin to go back the other way. Whereas, if you go round this curve, you go consistently round the origin in one direction all the time. We want to have some way of distinguishing between this sort of behaviour and this sort of behaviour. And I've got a machine that does exactly that. Here it is. Well, this arm here is connected to a spindle, and there's a string round the spindle which runs down and is connected to this pointer with a spring to keep it taut. If I turn the arm, then it pulls the string up and it moves the pointer. In order to see how much the pointer's moved, I'll put a scale behind it. So I'll put it so that it's on 0 now, and then if I turn that round, the pointer will move. You'll see how it works if I show you on my standard circle. Put it behind the machine so that the spindle's over the origin, and then if I trace round the curve, the pointer will move, and when I get back to where I started, it's moved up to +1. And that tells me I've gone round once, round the origin. I could now zero the scale again and try going round in the other direction. And this time, of course, it'll end up at -1, which tells me I've gone round once in the opposite direction. Well, so this machine is measuring the net number of revolutions around the origin that I make when I trace the curve. Let's try it out on our troublesome curve. Once again, I put the spindle over the origin and zero the scale before I start. And now, watch what happens as I trace the curve. Pointer's moving up and down, but when I get back to where I started, the pointer's on 0 again. So what we're going to do is to define the winding number to be what this machine measures. So this curve has winding number 1 because you go once round the origin as you go up the curve, go round the curve, and this one has winding number 0 because you end up not having gone round the origin at all on this scale. You end up with no net revolutions. So now we've got a definition of something which really measures the difference between this curve and this curve. This curve has winding number 0, and this curve has winding number 1. And I can measure the winding number for any curve that I can trace out with this machine. And of course, it doesn't matter if I follow the curve particularly accurately, it's just a sort of crude overall picture of the curve which is being measured, how many times it goes round the origin. But I can't measure the winding number for the curves I'm really interested in, the ones that pass through the origin, because they go under the spindle and I can't get my pointer in there. So, in order to see what happens to the winding number for those curves, let's look at our cubic polynomial once again. Here the winding number is 2. This time the box counts the winding number. Move on a little. Here it's still 2. When does it change? Here it's 3. Closer to the root, it's still 3. The winding number changes as the image crosses the origin. So what do we know about winding numbers? Well, the winding number is always an integer. It's defined for any curve that doesn't cross the origin. Nearby curves have the same winding number, and as you deform a curve continuously, the winding number does not change unless the curve crosses the origin. So now we can see how to repair the gap in our proof. You see, for this little curve that we started off with, if I put the pointer on it, it would hardly move at all. So the winding number is clearly 0, as we expect because it doesn't enclose the origin. For this big curve that I ended up with, for the cubic polynomial, it goes 3 times round the origin, so the winding number is obviously 3. And in general, for the nth degree polynomial, the big curve that we get is going to have winding number n. So, we just argue exactly as we did before, only instead of using the words enclosing the origin, we use the more precise term, winding number. You see, we start off with winding number 0, we end up with winding number n, and as we deform from here to here, the winding number doesn't change unless the curve crosses the origin, but the winding number goes from 0 to 3, so it must have changed, the curve must have crossed the origin, and so we must have found a root. And that's what we wanted to prove. Well, that's it. We finished the proof of the theorem that we set out to prove, and it only remains to prove the fundamental theorem of algebra that any nth degree polynomial has n roots. Well, perhaps you think that this proof could be patched up so as to actually do that for us. Because you see, the winding number changes from 0 to 3. Presumably it went 0, 1, 2, 3, as each of the coils of the curve crossed the origin. And so presumably we could count the 3 roots. Well, here's Alan to finish off the proof and also to explain why we can't argue in this way I've just described.
So we've proved our first theorem that a general polynomial has at least one root. But how do we go from there to the fundamental theorem of algebra, which states that a general polynomial of nth degree has precisely n roots? Well, it's quite straightforward. Well, here's my nth degree polynomial, and the theorem we've just proved tells me that I have at least one root, alpha 1. It turns out that that means that f of z factorizes in the form z minus alpha 1 into g of z. Now what's g of z? It's just another polynomial, this time of degree n minus 1. Why? Because z to the power n minus 1 times z just gives me z to the n, so everything's all right. But now I can argue about this polynomial in the same way as I did about f of z. And my theorem tells me that g of z has at least one root, call it alpha 2. So g of z itself factorizes in the form z minus alpha 2 into the polynomial h of z, which is again a polynomial of degree n minus 2. And well, you see I can keep on arguing the same way until eventually I have n linear factors. There won't be any more. And that tells me that f of z has precisely n roots. In fact, that's what we mean by saying it's got n roots. Now, what's the problem about the pictures? Well, the problem comes about with coincident roots. You see, not all of alpha 1, alpha 2, etc. need be different. For example, I could have a polynomial like this where both roots were 1. Now, in that case, there's no way that you're going to be able to distinguish between both of these roots on a picture. It's the same point. So we just finish the theorem by using a little bit of simple algebra. Well, I think that's fantastic. Only a short time ago, when we tried to solve a quadratic equation, we had to introduce a whole new concept of number, complex numbers. And with just the help of complex numbers, nothing else, we can solve every polynomial equation. I think that's wonderful. And it gives you some idea of the power of mathematics.